Okay, welcome back to energy resources and the second part of the lecture on biofuels. Now, basically, we are just about starting from here, manufacture from algae. Okay, now we'll move slightly away from the chemistry and we'll look at some of the technical stroke engineering aspects of biofuel in the closing few minutes of this lecture. If you grow crops in a field and you make them into biofuel, effectively you're using those crops to have taken carbon dioxide out the air, biologically processed it, and then you're accessing some of those biological products. Algae is a plant, that's exactly what it does, except of course you can use this on land that you otherwise couldn't use. There are positives and negatives. Effectively, the bit in the algae that you can use is inside here. You've got fatty acids, you've got lipids, you've got starch. So there's lots of things in there that you can actually use. Now, there are positives and negatives to using algae. Yes, they eat carbon dioxide, but actually you can feed them with sewage. Wastewater has lots of nutrients in, so you actually begin to get more than one benefit, because now you've potentially got a water cleanup system and a biofuel production plant. So that's good. Yes, extracts carbon dioxide from the atmosphere and can also produce methane as a fuel. So more than one biofuel, because gaseous methane is a biofuel, although we're not really talking about the gases in this lecture. But the negatives. It's okay to have all of these goodies popped up inside the algal cell, but it's actually quite difficult to break the cell to get those lipids out. Well, it's quite easy, but it's quite difficult to do it in a way without spending a lot of energy. And we'll think about this in a moment. If you're going to use this as a biofuel to effectively save energy, you have to be quite careful about how much energy you put in when you grow these crops, or break the cells in this case, to get your biofuel out. And potentially this can take a lot of land, although you can resolve that using so-called vertical algae farms. But more in a moment. The more goodies you can get out of a given process, the more economically viable it becomes. And in New Zealand, actually, the water cleanup is a really important economic goodie, because there's a very large dairy industry and water pollution is one of the major problems in some areas. So let's have a look at a typical biogas plant from algae, and this is for gases. We're not really going to talk about these very much, but I really want to just walk through this and highlight a few factors. So they have their algae growing here, and they're producing flue gas. They're introducing flue gas, so they're cleaning up a carbon dioxide emission for a factory or for a power station in this photobioreactor. So they're consuming the carbon dioxide to grow algae. They're then exporting the bioorganics. How they do that is something we'll talk about in a second. They're dewatering, which is the quite often expensive process. They're then methanating those products to give methane and carbon dioxide. They can either concentrate the carbon dioxide or put it back in here, but they produce methane. They can then take the methane out, or they can recycle some of it into a burner to produce more carbon dioxide and nitrogen, so that you have a system which is actually energy self-sufficient and cleaning up pollution. Now, this process here is potentially interesting because that's the problem. A lot of these stages you could find in an ordinary water cleanup plant, a sewage plant. But this is the energy process which is a problem here. And this could be replaced to make this system more useful. But we're only producing methane, which, okay, it's better than a poke in the eye with a sharp stick. But it's not a liquid biofuel, which is where we are really wanting to go. This now is work from the National Institute of Water and Air, which is like our SMART institutes. It's the Crown Research, one of the Crown Research Institutes in New Zealand. This is a related system which can produce biofuel, liquid biofuel. So again, you can put this on a sewage plant, wastewater, or you could feed it with a carbon dioxide stream from a factory or whatever. As well, additionally, you do an anaerobic digestion, which is what happens in sewage plants. You get fertilizers out. You take the resulting biogas, because you're not really going to export methane, and you burn it to produce heat and power. And then you take the flue gas, carbon dioxide and nitrogen, and you put it into an algal reactor, along with some of your original input water, which doesn't have the solids in it. You let this grow lots and lots of algae, and then you harvest the algae, and this is the clever bit. You don't actually, if you think about how you separate algae from water, how are you going to do it? I suppose you can filter it, very energetic process, or you can use membranes, but you still have to pressure the membranes, and that takes energy. And of course, every joule of energy you use is being bled away from your product. It makes it less useful. What they are doing here is they are using a very innovative piece of technology, a supercritical water reactor. So they harvest these algal cells without pre-concentration. The water goes straight through a supercritical water reactor, which breaks up the algal cells. The separation then is straightforward because it's immiscible with water. That then gets converted to biofuel, gets refined, and then exported. You get treated water at the bottom here, so you get purified water, and in the conversion process you produce more fertilizer. So this is interesting, and it's effectively pre-commercial. They are able to make a profit using this, and there's currently a deployment to New Zealand dairy farms, or some dairy farms, to obviously produce the wastewater and nutrient-rich broth that's needed to run this type of system. Right, so you need a concentrated source of carbon to do this, and here's a reasonably concentrated source of carbon. In fact, any cool part of the world where you have cows indoors for the winter gives you sufficient carbon, or of course you can use CO2 from carbon capture and storage systems. Let's think a bit more about that supercritical water. So here's a phase diagram. The trouble, supercritical water is pretty much got very limited use up until now. It's used for mineralogical syntheses, quartz crystals, mobile phones, gemstones, and the like. It's not like supercritical carbon dioxide. This stuff, you have to go up to maybe 375 centigrade and 700 atmospheres before you reach the region of the phase diagram where you have supercritical water. And this stuff isn't meek and mild, it's corrosive to steel, and a high temperature and high pressure. So actually it's It's not trivial to work with this. However, it's a very efficient way of breaking up these algal cells. And other advantages is it effectively dissolves the lipids and it makes the process much easier. Okay, final picture or two of this. This is actually, to give you an idea of what it looks like, this is a test bed I used to look out here from my office for some time when I worked in Christchurch. And these are actually oxidation ponds, and the sewage works its way along this long path to allow the algae to grow. You need lots of light, shallow ponds and the like. And even when you've finished, this is the final oxidation pond. Actually, you've got fish in there, you've got wildlife. It's actually a nature reserve. Very, very nice environmental results from these things as well. And you're producing biofuel. Okay, so an interim summary. The chemists and some others have provided and are providing tools and solutions to the biofuel problem. And the industrial sector is doing their part as well. The engineers are also producing good technology available to implement some of our chemistry. So, this could be a happy ending, couldn't it? We could move from fossil to biofuels. They say, never invite an economist for dinner, you'll end up slitting your own throat. The last 5 or 6 slides, we're going to ask, could it happen? This is our train journey, and we're now right at the end. Almost at the end. So, could it happen? Let's choose an optimistic scenario to see if we could make this happen. A very good scenario will be New Zealand. 40%, well actually 60% of that country is forested, 40% is in nature reserves of one sort or another. In a good year, 70% of his energy can be produced by hydro. Surely, of any country, this one has the possibility to become self-sufficient in a type of liquid fuel. And from now on, I'm stealing and plagiarising from the PCE work I did. So, let's say a type of liquid fuel. The best research questions are focused. So we need to choose which fuel. We know not all biofuels are the same. So we'll choose diesel because that's the fuel that drives the economy. And we'll choose wood-based biodiesel because actually there are a lot of trees in New Zealand. And if you replant, this is probably a 3rd generation biofuel. So excellent. Before we get all excited and rush off into the forest, we need to ask some slightly more penetrating questions. Assumptions. Make sure you look at them all. Is it actually saving energy? We're making biofuel, but actually, is it saving energy over the petroleum product? Is it drop-in? We'd prefer it to be drop-in so we don't have to do anything. Can we use it in our existing, in this case, diesel infrastructure? Is it economic? And can we make enough? So they're the types of question we're going to look at now. And please understand, personally, I'm very much an optimist. But some things don't turn out the way we would maybe like. Okay, so here we have a ratio which is important. It's the energy that you get out of the fuel if you burn it, divided by the energy you have to put in to make it. Now the black bars on both of these graphs are the same, and they are fossil diesel and fossil petrol. This, and obviously with that ratio, the higher this ratio is, that is, the smaller this energy input and the higher the output. So the taller these bars are, the better. And in this first panel, it's a bit depressing really. FAME biodiesel from canola, FAME biodiesel from tallow, that's animal fat, ethanol from whey, they're all quite poor biofuels really when you judge them against this yardstick. If we look at the second panel, there are some better ones here. Ethanol from wood is better, but actually the only one which is better than fossil diesel and fossil petrol is biodiesel from wood. Funny that. Anyway, so the two factors that we're going to use to judge these, well, a number of factors including economics, but first of all is this ratio, and our option of biodiesel from wood looked good here. And the second one, this is earlier work from Switzerland, if memory serves. And it looks at a number of different types of biofuel, and it adds up the different greenhouse gas emissions involved in the production. So the grey part of this thing is, where are we? The light grey is production, the dark grey is infrastructure, the black is operation, and the green is cultivation. So if you're growing biofuels, you've got to plant the stuff, you've got to add fertilizer, you've got to use tractors, and you've got to use energy in the production process. All of that's been added up here so that you can compare different biofuels. And the two black bars are Euro 3 diesel and Euro 3 petrol as standards. And you might be surprised, some biodiesels, of course, biodiesel's got to be better than fossil, hasn't it? So 100% soy from Brazil has greater carbon dioxide emissions than fossil petrol or fossil diesel. It's good to check these things out. Okay, so our biodiesel from wood, it ticks a number of our boxes. Basically, it's efficient in terms of energy in, energy out. It's efficient in terms of greenhouse gas emissions. One of the other questions we have to ask is, well, how much do we need? Can we make enough? This figure, again plagiarized from the PC report, for petrol and diesel show the annual amount of demand in New Zealand for these two fuels. These bars here indicate the amount currently being made by biodiesel. To be cynical, usually you need more than you have the capacity to make. We couldn't boost production of these to anything like the size of these bars. There aren't enough raw materials, there aren't enough plant, stuff like that. When you ask the question, how much can you make? Usually the answer is not enough. And then you have to ask questions about greenhouse emissions, which we did for a while. These are 2011 numbers, by the way. And effectively, this tells us that the current biofuels we're making will never be more than minor. The policy settings as well, and economically, it wouldn't make any sense to go that way. What we have established, though, what we did is I actually commissioned reports from companies that would have to do this, as to if we did go for biodiesel production from trees, from wood, how much would it actually cost? And how much could we actually make? So we set this up to make 120% of the New Zealand demand. And per litre of biofuel, the growing the wood, the logging, the hauling it, the chipping, and then the other factors in terms of a plant and making it, it came out as about 185, these are New Zealand dollars, per litre to make our biofuel from wood. And yes, We have easily the capacity to make it, and we even have the option to plant more trees so that it's carbon negative. And here's a note for any of you ever doing this. You actually have to have a very close regard to what really happens on the ground. I went out with these guys in their lorries to watch what they did so that the economics, actually cost-benefit analysis, and the economics could be robust. Okay, 185 then for a litre, and for that we also get replanting. 185 New Zealand dollars a litre is about 147 at this time, is about 147 US dollars per litre. It doesn't include delivery or transition costs, but for the most part transition costs are quite small because this is quite high quality biofuel, so it's dry, and it doesn't include delivery. So this is 147 US per litre at the factory. What's it competing with? Well, as of August 2016, crude oil is between $45 and $50 a barrel. Let's call it $50 a barrel, which is about 31 US cents per litre. If you go for production, because this is a produced product, it comes out at $0.95 per litre, and that's maximum. And of course, diesel has more energy content even than this high quality biodiesel. So if you adjust the price, effectively the US price is, for an equivalent product, is about $0.84. That's 84 cents a litre. I did say never invite an economist for dinner. They will depress you. What this means is this is not going to fly. It may be the right thing to do, but economically, at the moment, it's too expensive, partly because fossil fuels are so cheap. But you may say, hang on, there are other benefits. There's carbon costs. With diesel, you're producing carbon dioxide. With this biodiesel, you're not. Yes, okay. Unfortunately, with the most optimistic assumptions, you can add another 11 cents to the US price, which takes it back to 95 US cents a litre. So in fact, this is not going to fly. So you could say, right, we really need this to happen. So what we're going to do is we're going to subsidise our biofuel, our good biofuel, and we're going to subsidise it to the tune of maybe 52, 53 cents. So it's cheaper than the diesel fuel. Well, perverse outcome means if you do that, all that happens is your subsidised biofuel gets exported immediately and everybody makes a nice profit, except the government who is subsidising it. Subsidies are a temptation which you should not go for. Under certain, very strict, short timescale conditions, subsidies are possible. And if you don't believe me, I'll close with the example of Indonesia. Indonesia, a major oil producer, found that oil and fossil products were too expensive for its population to buy. So for exactly the right reasons, the aim of this subsidy, which Indonesia put on its fuel, was for its own citizens internally to make it cheaper and to support the poor in Indonesia. Unfortunately, if you make something cheaper, people think it has no value, and it was used very, very widely throughout Indonesia and is for everything because it's cheap. They have major health problems, air quality problems, into the billions because of their overuse of fossil fuels. The government's impoverished. This subsidy is costing about $4 billion a year US, which is about 10% of their state budget. The United Nations looked at this subsidy, and I won't read it. they and the OECD together basically agreed that this does not make any sense. Subsidies long term is almost certainly a bad idea because human beings are human beings. These are the words of the United Nations Environment Programme on subsidies, particularly the Indonesian subsidy. Okay, I think we'll close this lecture now, and I'll close it in the way I began the course. This slide you've seen before, and it's really talking about energy studies, energy resources, with fundamental chemistry underneath it, is a potential game changer. There is the status quo, and we know what that looks like. Our world is a beautiful place, stunningly beautiful, but it can be a terrible place as well, where 70 or 80% of the world haven't got enough to eat, and in other parts of the world, overeating is a problem. Anyway, you're chemists. Take some economics as well, but go and change the world. Thanks a lot. Bye-bye.